A very nice welcome by Bharatiya Kisan, Indian farmer and Aryavartian Krisak and quantum Krisaks, quantum farmers and quantum Kisan. And today in this lecture we are going to see some application of uncertainty principle. So let's see these applications. First, the path of an object. To define the path of a particle in an exact manner, we know that its exact position and velocity simultaneously should be known. Such a knowledge is not permitted by the uncertainty principle. Hence, the path or the orbit of an object in quantum physics is not defined. This invalidates Bohr's theory of the hydrogen atom, which assigns position and velocity simultaneously to the orbiting electron. Next application, angular momentum of an object. The angular momentum L vector, the angular momentum L vector of an object, angular momentum is a vector quantity of an object is defined as a cross product of its position and momentum. Since position and momentum are not known simultaneously, angular momentum is also uncertain. However, but we will learn later, L square, that is L vector dot L vector, can have well defined values. Next application, the size of an atom. We can use uncertainty principle even to determine the approximate size of an atom. Consider the example of the hydrogen atom. A hydrogen atom has a proton and an electron. If we assume the size of the atom to be A, then the uncertainty in the position of the electron is about A. That is, the electron is inside the atom. Hence, according to Heisenberg uncertainty principle, the uncertainty in the electron's momentum is given by delta P equal to h cut by A. The total non-relativistic energy of the electron is E equals to P square by 2 m naught minus E square by 4 pi epsilon naught A. For a stable atom, E will be minimum. Hence, we have to replace P by h cut by A and equate dE by dA to 0. That is, dE by dA equals to 0. And from this, we get A equals to 4 pi epsilon naught h cut square by m naught E square equals to 0.5 angstrom using all given value. And the corresponding value of energy E, comes out to be minus 1 by 2 m naught E to the power 4 divided by 4 in bracket 4 pi epsilon naught to the power 2 h cut square equals to minus 13.6 electron volt. The negative sign of the energy shows that electron is bound to the proton. So we will note that these values are in good agreement with the experimental data. Now next we see the existence of electron inside the nucleus. We have used the uncertainty principle to show that the electron, earlier we have used the uncertainty principle to show that the electrons do not exist inside the nucleus. The size of a nucleus is of the order of 1 Fermi, that is 10 to the power minus 15 meter. Therefore, if electrons are present inside the nucleus, then the maximum uncertainty in their position is delta x equals to 10 to the power minus 15 meter. Hence, delta P will be h cut by delta x equal to 10 to the power minus 19 joule second per meter. The total energy may be obtained from the relation E square equals to P square C square plus m naught square C to the power 4, or E equals to PC, as m naught C square is very less than PC. Thus we have E equals to 3 into 10 to the power minus 11 joule equal to 200 mega electron volt. But experimentally we find that during the beta decay of a nucleus, electron of energy between 2 to 3 mega electron volt, 2 to 3 mega electron volt is ejected. Hence we conclude that electrons were not present in the nucleus before they decay. Now next is zero point energy. According to kinetic theory, the kinetic energy of atoms oscillating about their position in crystals are proportional to the absolute temperature. Hence, at absolute zero, the atoms, according to this theory, would stop oscillating and would remain fixed in their lattice position. But according to uncertainty relation, both position and momentum cannot be specified at the same time with complete accuracy. This means that the atomic oscillator, even at absolute zero, would retain a certain amount of oscillatory motion, enough to obey the uncertainty relation. The energy possessed by atomic oscillator at absolute zero is termed as zero point energy. Experimental study of the motion of an atom at temperature 0.001 Kelvin, quite close to absolute zero, have shown the reality of the 0 point energy. Now let's see some important points related to this lecture or this whole lectures, that is matter waves and uncertainty principle. The first point, wave particle duality and the localization of the particles lead to the representation of a particle by a group of wave called wave packet. The group velocity v sub g of the wave packet is equal to the particle velocity v, and the phase velocity v sub p is given by c square by v. Next point, the concept of a wave packet leads to Heisenberg's uncertainty principle, according to which two canonically conjugate variables like x and p sub x or e and t cannot be simultaneously determined with perfect accuracy. The product of the uncertainties associated with these variables, that is delta x, delta p sub x, and delta e into delta t, is of the order of the Planck's constant h, that is delta x into delta p sub x greater than equal to h cut, or delta e into delta t greater than equal to h cut. Next point, some of the notable consequences of the uncertainty principles are: first, the path of a particle is not defined in quantum physics. Electrons do not exist inside the nucleus. Atomic oscillator possess a certain amount of energy known as the zero-point energy even at absolute zero temperature. Several thought experiments such as the gamma ray microscope experiment, the single slit diffraction experiment, and the double slit experiment have helped in formally establishing the validity of the uncertainty principle. With this, I would like to end this lecture.